Hello, everyone. My name is Daniel. So, as mentioned, I'm going to be talking about the productive use of ponded coal ash and its beneficiation. This work has been sort of passed around from professor to professor, grad student over the course of a couple of years. So, there's a lot of names on this presentation. Okay. So, first of all, just the basics. Fly ash is a byproduct of coal combustion and is currently the most widely utilized SCM in the world. It provides improvements to late-age compressor strength, workability, speed of hydration, and improves resistance to chemical and weather effects. Additionally, its status as an industrial byproduct allows for a reduction in embodied CO2 emissions and reduces the cost of construction. Now, there is a pretty big issue that the industry as a whole needs to address, and that is the increasing use of natural gas and renewable energy is leading to an industry-wide shift away from coal combustion as a source of power. And this has led to a nationwide shortage in fly ash supply. Now, the construction industry highly depends on fly ash in order to maintain the quality of its infrastructure, specifically in terms of the alkali silica reaction. So there is a very high need in this country to find a new supply of SCMs to compensate for this drop in fly ash supply. Now, as it turns out, only about half of all fly ash produced is actually beneficially utilized. The majority of this material is rejected, mostly due to a mismatch in supply and demand, where the majority of fly ash produced in this country is during the winter months when construction slows down. So this rejected material is stored in coal ash ponds or in landfills, and the American Coal Ash Association estimates that over 2 billion tons of coal ash is stored in ponds around the country. Now, this image here shows the liner status of over 738 coal ash ponds in 42 states. The black dots show unlined units, yellow dots show unknown liner status, and the green dots show a properly lined coal ash pond. So if you look at it, you'll notice a trend, and that the vast majority of these coal ash ponds remain unlined. And in fact, the majority of them, actually around 90% of them, are actively contaminating groundwater sources at levels exceeding that of federal guidelines. Now, in 2015, the EPA released new regulations requiring the closure and relocation of any coal ash ponds actively contaminating groundwater sources to properly lined dry storage facilities. And as I just mentioned, that means nearly the majority of these coal ash ponds will need to be closed down and relocated. So this process will, of course, cost billions of dollars and take many years to accomplish. However, since I said at the beginning of this, the majority of the coal ash that's stored in these places aren't rejected due to poor quality. It's just due to a mismatch in supply and demand. So it may be possible to reutilize this material as an SCM instead. So in order to test this, we took 13 ponded coal ash samples collected from 4 different power plants. All of these ashes were derived from eastern bituminous coals, likely in Class F fly ash. The PM ashes were collected from beds of up to 5 feet deep. They're less than 10 years old. These ashes were typically rejected due to historically inconsistent quality. The PW ashes were taken from up to 2 feet deep and were rejected due to a lack of market demand. The B ashes were taken from deep depths, 10 to 15 feet deep, and were less than 20 years old. And finally, the Y ash was collected at shallow depths, and this plant possessed no dry collection capacity, so all ashes produced were eventually placed in ponds. Presented here is the oxide composition of the 13 coal ashes and the reference Class F fly ash determined via X-ray fluorescence. There's a lot of numbers here, so there's only a few things I want to note. The first is the sum of primary oxide contents for all these samples, in this row here, are all about 90%, give or take a percentage point or two. Calcium oxide content, similarly, doesn't really go above 3%. So we have all of these samples are Class F fly ash, as they would be identified. In addition, we have a very low sulfur content, so unlikely to have any gypsum contamination, and the equivalent alkali content is fairly similar to that of Class F fly ash. Some things I want to mention I should point out, is the loss of ignition. Particle size, average particle size of these samples are very large and very variable in nature. And we believe that tends to be due to the commingling of bottom ash with the fly ash. In addition to that, the PW ashes and the V ash especially have elevated levels of iron, in cases reaching up to like 37%. And that'll be important later. Just wanted to point that out now. So here is the particle size distribution of these tested ashes as determined through wet dispersion, a laser particle size analysis. This is plotted in comparison to a commercially available Class F fly ash, which is this black line you see here. And the PW and V ashes are fairly comparable in terms of distribution to the classic fly ash, whereas the CM ashes and the Y ash are actually quite a bit coarser. The Y ash in particular shows a greater presence of oversized particles, which I believe to be due to the presence of agglomerated clay particles, which contaminated the sample to the pond subgrade. So, in order to test these ashes properties, we prepared some 2-inch mortar cubes for compressive strength testing. I blended some cement paste for isothermal calorimetry to be measured at 25 degrees Celsius for 48 hours. And finally, we did some accelerated mortar bar tests, ASTM C618 to measure the alkali-silica reaction mitigation potential. All these mixes were blended at 20% replacement by weight and were measured at a constant water to binder ratio for each test. So this graph here shows the relative strength of each sample at 7 and 28 days. The solid bar shows the 7-day strength. The dashed bar shows the 28-day strength. And with this solid horizontal line showing the minimum ASTM C618 limit, 75% at 7 and 28 days. As you can see, 4 of these samples out of the 13 fail compressive strength requirements. They actually get a quite low compressive strength. On the other hand, a lot of the samples actually perform quite similarly to classic Class F fly ash, and in some cases even outperform it, in the case of PM1 or V2, for example. Something I should note is that in some cases the relative strength does decrease with the progressing time, which indicates a low level of reactivity in that particular fly ash sample. Now, something that we wanted to determine for these 4 failing ashes is why exactly these 4 ashes in particular failed. So what I did is I separated out these samples to passing and failing properties, and I plotted the loss of emission, the x-axis, and total organic carbon content, the y-axis. And as you can see, once you get to about 8% loss in ignition, the majority of the ashes starts to fail. In addition to that, a lot of the ashes that are significantly off the 1-to-1 correlation line between the 2 properties also fail, indicating a significant presence of hydrated bases present in the samples. There's one exception to this rule, which is this one PM1 sample shown right here. We believe that one passed due to its somewhat unique particle size distribution, which led to greater than usual particle packing effect. This table here compares these 13 ponded coal ashes to ASTM C618 requirements for Class F fly ash, shown in this column here. And as you can see, 6 of these ashes fail due to a combination of loss in ignition and compressive strength, which we believe to be heavily related to each other, along with particle size and fineness, shown this fineness property. Now, these failures seem to be, relatively speaking, pond dependent. The PM pond, for instance, performs very poorly, but the PW pond overall performs relatively well, with only one ash out of 5 doing poorly. So that could be a very relatively simple way of identifying high quality or decent quality coal ashes. Now, shown here is the cumulative results for the isothermal calorimetry assessment tested over 48 hours. The dotted blue line here indicates the control mix, 100% Portland cement. And although it is very hard to see, somewhere in this cluster of lines is a dashed orange line, which indicates non-reactive quartz. Now, with The thing with Class F fly ash is that it reacts very slowly. So what we'd expect to see is a level of heat release around that, clustered around that of non-reactive quartz. And that is the case for most of these samples. However, 3 of our ashes, CM1, 2, and the Y ash, actually exhibit elevated levels of hydration. So why is that these samples show higher hydration heat? So on the on this graph here, I plotted the cumulative heat at 48 hours for each of the samples, and on the x-axis, I plotted the loss on ignition, with this dashed orange line being the non-reactive quartz, the heat released by 48 hours, just reported as a constant. As you can see, once you get to about 10% loss of ignition, you start getting elevated levels of hydration heat. Which we believe potentially to be due to a artificially low water to binder ratio, where the presence of unburnt carbon absorbs water, therefore creating an artificially low water content. Finally, what we have here is the accelerated motor bar test, measured for these samples up to 14 days. This solid black line here shows the maximum expansion limit, 0.1% by the end of 14 days. And interestingly enough, what we have here is sort of a reversing quality, where the PW ashes and the V ash, which up to this point had been performing quite well in terms of comparison to ordinary fly ash, actually fail these requirements, whereas the PM ashes actually perform quite similarly to the comparison Class F fly ash. And we wanted to know, again, why that happened. And it turns out, we believe that it's due to the composition of the primary oxide. You'll remember from an earlier slide that I had mentioned that all of these samples have a primary oxide content of about 90%, give or take a couple percentage points. However, a lot of these samples possess elevated levels of iron, in most cases, a lot over 20%. And in those cases, you can see a very distinct separation between passing and failing ashes, where all the failing ashes have elevated levels of iron and relatively lower levels of silicon aluminum, which have been identified in previous research to be the elements more effective at mitigating the ASR reaction. So to sum up these findings, some common issues that you'll run into with pond and coal ash. The first is typically you'll run into a large loss on ignition, which can cause low strength and high heat of hydration if left unchecked. Second is a potentially large iron content, which can interfere with your ASR mitigation potential. Large particle sizes can affect early gauge strength, and low reactivity can interfere with strength development. Now, potential ashes will, of course, need to be watered, and while it was not an issue in our case, there is a potential for the presence of flue gas gypsum, which is created as a byproduct of the desulfurization of the flue gas stream, and that can affect setting time if there's too large a quantity. Now, this analysis that we did suggests that the quality of these ashes tend to be pretty pond dependent, so a simple XRF particle size analysis may help with identifying good quality ponds, whereas low quality ponds may need to be beneficiated before they can be properly utilized. So to discuss this potential, I will introduce this process that I'm currently investigating called chemi-mechanical grinding. Currently have a short communication review by Fuel on this topic, so if you want to learn more, wait till it gets published. But this process can solve a number, not quite all, but a number of these issues typically present with pond coal ash. Now, traditional mechanical grinding is used to reduce the particle size distribution of the material, so that solves that problem right off the bat. The mechanical action of the grinding process breaks down crystalline structures in the material, thus increasing amorphous content, increasing the quantity of reactive phases, and that helps solve strength development problems. However, we believe that this traditional grinding process, when in the presence of relatively large quantity of water, can provide additional benefits to this process. And that is that conditions that this grinder is under, that is high heat, relatively high pressure, allows for siliceous materials to undergo hydrolysis when in the presence of water, that is chemical reaction with water. When that happens, you'll see silanol groups form on the surface of these silicious materials, present with this hydroxyl branches you see here. And that's the chemi portion of the chemi-mechanical bragging process. Now, these silanol groups have the capacity to react very quickly with calcium hydroxide. And this allows the silanol to essentially behave like reaction sites for the pozzolanic reaction, thus increasing the reaction rate of the final product. So this is just some basic analysis of this process. We've managed to get that much done so far. But we took 4 of the failed ashes that failed compressive strength requirements. That is PM2, PM4, PWD10, and the Y ash. We blended them with a good quantity of water to reach a muddy consistency, and then we placed them into a shaker ball mill for 1 hour at 25 hertz. And then we did some basic analysis using X-ray diffraction, scanning electron microscopy, and attenuated total reflectance to identify the silanol groups. So first, with X-ray diffraction, we blended in 10% lanthanum hexaboride as a reference material in order to quantify the amorphous content of our material. We saw, in general, that the grinding process increased the amorphous content by between 5 to 36 percentage points, or 7 to 70% increase in amorphous content, in other words. And this mainly comes from a breakdown in quartz and molybdenum. So that, again, suggests an increase in reactive phases and amorphous content. Though I should note, one sample, PW10, didn't improve much at all. It only received 5-ish% improvement in amorphous content. And we believe that this is due to the high quantity of iron in the sample. We believe this sample in particular had like 35% iron and 12% of these iron-bearing phases, hematite and magnetite, which under these conditions don't seem to break down. So we did observe a conversion of hematite to magnetite during the grinding process. Next, we have scanning electron microscopy. We analyzed one of the samples, sample PM2, between 20 and 15 micron magnification range in order to observe changes in size and morphology. Now, right here, left column, we have sample PM2 before the grinding process. The right column is the sample PM2 after the grinding process. Now, before grinding, it's easily identified as these spherical and spherical morphology characteristic of ordinary fly ash. And we also get these impurities, these large sponge-like materials, which we believe to be unburnt carbon and in some cases some organic. So it does seem to be a fairly ordinary fly ash, but it's fairly dirty in that mind. Now, after the grinding process, those spherical morphologies and the unburnt sponge-like carbon morphologies are no longer recognizable. It gets ground down, and now the ash is composed of a large, smaller particles fused together into larger agglomerations. Now, these smaller particles will be more reactive due to an increase in surface area, but we might lose some workability due to the loss of sphericity and, again, due to the increase in surface area. Finally, we have the attenuated total reflectance, which we used to identify silanol groups. I should note here that I personally did not do these scans. This work was done by another postdoc, so I'm not super familiar with these graphs. But so right here we have the ATR results for the 4 different ashes. The dashed line indicates the samples before the grinding process. The solid line indicates the samples after the grinding process. Now, the exact magnitude of the height of these scans don't matter all that much. It mainly depends on how much of the sample is placed into the scanner. So that's not quite as important. But within this orange region here, we can generally observe a broadening of the peaks present, which correlates with a general increase in disorder among the mineral phases. And that suggests more amorphous content, more reactive phases. And that is in agreement with my X-ray diffraction results. Now, most interestingly, at the 800 mark, we see the formation of these 2 sharp peaks in some of these samples, and all these samples actually. And that is the formation of the silanol groups that I was mentioning before. Notably, sample PM4 and the Y ash formed greater quantity, the silanol peaks in those two samples are much sharper, so they formed more readily than the sample PMP or PW10. And we believe that is because of the presence of excessive carbon in those samples or to the presence of the excessive iron in those samples, which absorbs water or reduces the quantity of silica available for conversion. But the formation of these silanol groups does suggest an increase in reaction rate at the final product. So, some final thoughts. This beneficiation process will improve the particle size distribution and reactivity issues characteristic of ponded coal ash. This process can be done and should be done at higher water content and can thus help reduce the cost of dewatering. I didn't actually include this information in this presentation, but we found that for our samples, the water content actually got reduced between like 20 and 50%, I believe it was. And the resulting product should perform relatively consistently well in comparison to the source material. Fortunately, this process doesn't solve all the problems associated with this material. We believe that there may be a negative effect due to workability, due to the often fly ash shape and increase in surface area. And I understand that in previous research, reduction loss of emission was recorded, but the presence of water probably does interfere with that to some degree. Overall, though, we believe that this beneficiation process will allow for even more of the ponded coal ash samples to be beneficially utilized. I'd like to thank you all for your time. Take any questions you have.